What we will do in this class is we will quickly go through the, okay, let me share the video as well here, share the screen. Okay. Is it clearly visible? So what we will do in this class is we will quickly go through the recorded video that has been posted yesterday, and then we will continue our discussion with some illustrations. Okay. So the basic concept that we were discussing in that video is you have a continuous time signal. We started with a 1D signal. You have a continuous time signal for which you have a Fourier transform. Now, the question that we are posing ourselves is, suppose instead of this whole continuous time signal, I am keeping only samples of the signal instead of keeping the signal, keeping track of the whole signal at all points, which is of course infeasible when you are doing it on a computer, right? So now, once you are taking samples of the signal, you get some new Fourier transform, right? How is this Fourier transform related to the Fourier transform of the original signal? And then is it possible to get back your original signal from this Fourier transform, provided you are taking enough samples of this original signal? This is the key problem that we are trying to address. So how we did that, say here you have a f of x is your signal. So then you had the Fourier transform of it. The assumption is it is a band limited signal. If not, you will make it band limited, let's say by applying a low pass filter. And of course, in that case, what you get back will not be exactly equal to your original signal. What would you get then? Is the question clear? So we are assuming it's a band limited signal. So the next argument we are making is, if it is not band limited, we make it band limited by applying a low pass filter. Okay. And then you do the whole process, and then from that you could get back the signal. So what is the signal that you would be getting back there? Right. So yeah, you could, I think maybe Notana, I think the answer is correct. It's like what you get is a smoothed image, right? Because the low pass filtering is like applying a Gaussian filter. So it's equivalent to convolving your given 2D image with Gaussian smoothing, right? You get a smoothed or a blurred image, right? So you have this. Now, in order to get samples of it, we are looking at in terms of what is its equivalent in mathematical terms. It's equivalent to multiplying with an impulse train. Once you do that, all you will be left with here are just its values at some regular points, right? So then we are looking at what happens to its Fourier transform. So multiplying with an impulse train is equal to multiplication in the spatial domain is equal to convolution in the frequency domain, right? So you are going to convolve it with this impulse train. So impulse train is basically, you could think of shifted, a summation of all shifted impulses, of course at 0 plus all impulses that are shifted by, if the sampling is, if the original impulse train samples are taken at x naught, here the placing will be an integer multiple of 1 by x naught. So that's what it is going to happen. So convolution with a delayed impulse, what will it do? I have a signal, I'm convolving it with a delayed impulse. So what would happen to the signal? Is it nobody's microphones are working? What would happen when I'm convolving a signal with a delayed impulse?
It will get repeated after certain intervals.
No, just I'm saying you are just convolving with a delayed impulse. What would happen to the signal?
It's shifted, sir.
Sorry.
It gets shifted.
Right. The signal also get delayed by the same value, or it gets shifted by the same delay. Correct. So that's exactly what would happen here. And that's what we were looking at here, this original signal. Since Now impulses convolving with impulses. Originally, if you are taking samples at a distance of x naught, here it's equivalent to convolving with an impulse train where the distances are 1 by x naught, 2 by x naught, 3 by x naught, and so on. So you have each of these Fourier spectrum placed at integer multiples of x naught, right? And then what you have to do further? Well, in addition, one more effect is also taking place. Impulse train, if you take it, the Fourier transform also has a multiplication factor. So I hope everybody is very clear with what is the continuous time Fourier transform of an impulse train. Okay, if not, you could go to the DSP recorded videos. There will be one video exclusively on dealing with impulse trains, both in the discrete time Fourier transform and continuous time Fourier transforms of impulse train. Okay, there I was discussing both about continuous time Fourier series of impulse train. That's where I started with, and then I would be discussing about continuous time Fourier transform of impulse train. And also, to be strict, as you are seeing in the other speech signal processing, I should not be calling in the discrete time domain that impulse train. You could call as a unit sample train if you want. Okay. Anyways, that also you would see in that. Okay, that you have to be very clear, right? So, anyways, coming back here, this 1 by x naught is the magnitude also is getting scaled by 1 by x naught. So what I would be doing now is applying a rect function here, for example, and then this should have a magnitude of x naught instead of 1. So you do an amplification of x naught. And then another point we were discussing is how much should be this you normally refer to as sampling rate once it comes to 1 by x naught. So this sampling rate, how much it should be, that's what we were discussing here. So you could see here, this is XL. So the other negative side of this also copy placed here has XL. So assuming that XL is the maximum limit on what the frequency you are having. So unless this distance is at least equal to 2XL, ideally more than that, there is an overlap. And once there is an overlap, high frequencies and low frequencies are getting merged up, and then you won't be able to recover back your original signal. So what we are is what has to happen here, this 1 by x naught, the sampling rate should be at least equal to twice the value of the maximum frequency that you are going to have here. So this is the famous Nyquist theorem that tells you with what rate you should sample the signal so that you could get back the original signal, provided of course it's a band limited signal. Okay, hope everyone is fine with what we discussed so far. If so, I would move on to the next part, 2D, moving to extending it to 2D. Okay, now I assume no one has any question. Right, now you want to take samples of a 2D signal. It's not 1D signal. Okay, so you want to take it at regular intervals. So for these regular intervals, what you would like to do is you would like to annex in what increments you would like to change, and across Y with what increments you would like to take the samples of it. So to do that, now you need something like this. Okay, although I was calling in the recorded video lecture this one as an impulse train, that's definitely not the right way, because there is not one train here. Okay, at each row there is one train. So yeah, a crude or a not so sophisticated name is to have a bed of nails here. Okay, so basically you have a grid of impulses. Okay, that's probably more polished way of saying it, right? This is what you have, and that's what your this is what with which you need to multiply your function. So we are trying to write the mathematical expression here. As you could see, you take one value. If you want, you just for the interpretation, just you put n here and m here, and then see here, this is for example n equal to 0, n equal to 1, n equal to 2, and so forth, so on. And this is n equal to -1, n equal to -2. And then for each n, you are varying m value from -infinity to +infinity to, so to the from the left to the right. Okay, of course this also you could do the interpretation, but now you see it in terms of columns. That's also should make sense. Okay, and then having different, you could have, by the way, what is it that decides or that have an influence on what should be the values of the sampling rates in the x and y directions? What is it that has an influence on deciding what should be the x0 value and y0 value? I don't think it's a tough question. You, most of you should be knowing the answer, I guess.
XL and YL.
That's it. XL and YL. That's all. Right. So whatever you have frequencies now, earlier it was just XL you have it. Now YL is there. So XL will dictate what should be your, because these copies are placed both along X and as well as Y. Depending on XL, you should decide on what is in good enough value of 1 by XL, right? Similarly, YL should tell you the frequency spectrum kx ky. On the ky, for example, here this value should tell you how many copies you could place there, right? That's the frequency spectrum. In other words, the frequency spectrum of f of xy is that which governs or which influences the ideal or the minimal sampling rate that we should have along x and along y, right? Okay, now coming back here, so this is your function where it is varying. I think you got the interpretation of this function quite well now by this time. Then you could see the Fourier transform you could apply. You already know the Fourier transform, 2D Fourier transform expression. This is quite straightforward there. These are separable in fact, right? You could write it as del, yeah, this multiplication kind of thing. You could write this one as, and then you move them both here. So that would eventually could give you 1 by x. So yeah, just like extension earlier, when you have this function alone, you had 1 by x naught and integer multiple of 1 by x naught here, right? So you have this also that would additionally give you multiplication of 1 by y naught. These were separable impulse functions that you could write it as sequence of impulses there. So then 1 by y naught and n by y naught, that's all. So what you are going to have here, one more bed of nails now, whose distance along the x-axis is now instead of x naught 1 by x naught there, and along the y-axis instead of y naught you have 1 by y naught there. And of course then the magnitude of those impulses getting multiplied with 1 over x naught times y naught, correct? So then in order to get the samples, you are going to multiply here, the same story here. Now you are on the Fourier domain, it's equivalent to convolving it there. So again, it would keep copies of it the moment you are convolving it. So you would be, yeah, it is not going up, that's okay. So that's why you would be getting here the copies of it delayed, again sifting property, not shifting, it is shifting, right? Everybody knows SIFTING, it's like picking up what you exactly want anyway. Okay, so f of kx minus m by x naught, this gets shifted, and then this shifting integer multiples of x naught and y naught, it varies. So this is how you could have along x-axis there is a distance of 1 by x naught, and copies are placed along y-axis with a distance of 1 by y naught. This you assume as some intensity. Okay, this is now 3D. Earlier we were happy drawing things in 1D, so that's okay. I know you all know it by this time. Okay, so what should happen now? This 1 by x naught should be at least twice the XL. Similarly, this 1 by y naught should be twice the YL value there, right? Is everybody fine with it? If there are no questions, I'll continue with some illustrations for sampling. Or maybe I'll repeat, in fact, some of them, but with a different, slightly different way. Okay.
So,
Yeah.
like if there's the sampling theorem is being followed only in one dimension, say only in the x. So, and in y there is aliasing. So can we recover just the x component of the original signal?
Good question. Does anyone have an answer for this? Anyone would like at least give it a try?
Sir, what was the question, sir?
Yeah, can you repeat, Shashwat?
Suppose if there's aliasing only in one direction, say y, but in the x direction there's no aliasing. So can we recover just the component of the signal which does not have aliasing, like the x component? That's the question.
Sir, it depends on how much the signal is aliased in bi-direction also.
No, he's saying there is no, no, that's a, no, that's,
Sir,
yeah.
if f of xy can be written as f of x into f of y, then
Is it possible then?
maybe independent.
See, let me see it in a way. Can I rephrase this question as, suppose if I take each row, okay, that's along x-axis, will the values be same? Is it not the same question, Shashwat? So your question boils down to row wise. My x is this, my image assume that this is my x and this is my y. So is your question equivalent to saying that if I look row wise, all the values exactly same or not?
Yeah, just as the original signal. Maybe
now that itself has the answer now. So you look at it in the other way. Suppose your values are changing along y-axis. So then can now when you are looking at it along x, will that be same now in that row? No, is the logic I'm trying to put forth, is it clear? See, your question boiled down to, if I take row wise, okay, then I'm looking at values in the x direction. Okay, so your question is there is no aliasing in the x direction, so every x should assume that it is correctly shown. Okay, now that what would happen now? For example, if it is happening for every row x wise, then obviously it should happen for y also, is it not?
yes, sir.
So it means it doesn't happen. Now the way you could think of it is, you see there is you are representing your f of xy. If you recollect the kind of representation we made as a linear combination of your kx and ky's, right? Some different sinusoids, varying intensities and all. So all it would perhaps would do is the weights for those varying along x-axis would be the same, but the y is changing. But at the end of the day, you are looking at any signal that is obtained as a combination of all of them. So that will not be the same thing. In terms of weights, if you look at each sinusoids, one that it is contributing to, half of them could remain the same weights. But at the end, the signal will be different. See, even adding one ky along, adding one new frequency would alter all the values of that image, the whole image, right? So this would have an impact over the entire image. But if you look at in terms of decomposing them into frequencies along x and y, then the weights given to x might not change, but y would change. That's what I feel. Is it not?
So, yeah, yes, sir. Even though like if the weights along y change, we can't ultimately recover the original signal anyway, right?
That's right. So that is why we should not be having any aliasing happening in any of the directions. It should be aliasing free in both the directions.
Yes, sir. Got it.
Yeah. Hope that explanation makes sense.
Yes.
Okay. Good. Any other question? Any other thoughts here before we?
Sir, is it because we can't recover the signal back if aliasing happens?
Right.
or
So that's the biggest problem. The moment you have an aliasing, you can never recover back the signal. See, we are going to see, of course, right now we are talking about aliasing in the frequency domain only. Then again, there is an aliasing in the time domain also. For all your operations, what you are doing now, you are going back and forth of the spatial domain and frequency domain. The moment aliasing happens either in the spatial domain or in the frequency domain, it's no more useful for you. The moment you come out, the guy who goes inside the room and comes out, they are two different people. Okay, so you won't get him back.
so what if we had passed it through an LPF before?
Sorry, your audio is bit low. Sorry.
Sir, what if we had passed it through a low pass filter before
Right.
taking the Fourier transform?
Exactly. So that was my first question I was asking in this class. So what was the effect of it? See, when you, what was the effect of it?
Image got smooth.
That's right. You get a blurred image. See, if you have no control over the rate at which you could sample, the only best thing that you could do is to smooth the image and get rid of high frequencies. And that is how to, but the moment you are applying a low pass filtering there, it's, for example, Gaussian smoothing is a way of low pass filtering. So the details, high frequency content is the one which contributes to constructing the sudden changes, which in other words, most likely the edges in a given image are a fine texture that you have in a, or a slight variations that you have, finer variations you have in the image that you are going to lose.
Okay, sir.
Okay, good. Any other doubts or thoughts here? That is what you would be doing. I'll show you an example also on the same point as we move on. And of course, we had this example in our computer vision course also, but I would show you slightly different example here. Okay, so with that, maybe if there are no questions, I would move on to few slides here. I wish this nicely fits to the top, but no. Okay, right. So yeah, this is part 2. Okay, this is just, rather than entertaining you with my drawings, I'm just showing here more professional ones. Okay, so you are, this is a comb function. You are, in order to get samples of it, you are multiplying with them, and then your sample signal is nothing but an impulse train multiplied with f of x. This f of x has been taken inside. Okay, since I already covered, I'm going it as if you all know it, but if you have any question, just stop me there. Okay, so now here I wish this, everything is coming on the way. Okay, this is better. Right now 2D equivalent is what we are writing there. Instead of having one comb there, you have bed of nails there, both varying in x and y. And then Fourier transform pair, if you look at it, just in case of this, where there are impulses placed at an integer multiples of x, you take Fourier transform of it. Now they are placed at a distance of integer multiples of 1 by x. Not only that, if they are placed at a distance of x, you have a multiplication factor of 1 by x. Now you have summation of these two, this bed of nails. Now the same thing would repeat. Now x and y, they are placed, multiplication of 1 by xy, and this is what you would be getting there as a Fourier transform pair. Then for sampling in 1D, okay, so what you are doing, you have this function, so you are multiplying it with impulse train you to get these points. That's equivalent to convolving your original one with an impulse train again, so which would again keep copies. Each one would make this shift to that particular center. This center would shift here, so you would be getting something like this. And then you could write the expression. Yeah, again, from the ones I don't exactly remember also the source for this. Sorry for that. I took this in the last year, some slides, so I should have made a note of it, but I think it's okay. Yeah, again, this credit doesn't belong to me for these credits. I took it from somewhere else, like I was doing for other topics also. right? Okay, coming back here. So this would be equivalent to, now you are trying to write the Fourier transform expression for this. Okay, so what is this equivalent to? You have the original one placed at multiple places. Each one is separated by a distance. If you are taking samples at a distance of capital X, now these are separated by a distance of 1 by X, right? And the whole thing magnitude is getting multiplied by 1 by X here, right? And what you have to do now is you have to take just one copy of it is required here. Low pass filtering with a rect function is what you have to do here, right? So then what should be this rect function? So he's taking this as, let's say, 1 by X itself, right? One whole copy of it, he's taking it. So that if you write it in terms of rect function, this is rect of kx into x. So it will be from minus 1 by 2x to 1 by 2x. So you write it as rect of k, wherever u is there, use k subscript x there. Okay, that's the kx we are using, k subscript x of x, correct? Then you are multiplying it with the rect function. That's equivalent to what? What is it equivalent to in the Fourier domain? Sorry, in the spatial domain. So you want a one copy of it to construct it back here. Okay, so what is its equivalent function in the spatial domain now? Hello, you should be remembering this. I'm sure many of you know this, right? We have been seeing it in different places so far. So one way is, I was just comparing earlier that this is nothing but your Fourier transform of the original signal. But I am putting this question now mathematically, where I am asking you that multiplying this with rect function, this one, what is it equivalent to in the Fourier domain now? That's the question.
Convolving with sinc function.
Right, convolving with sinc. Which function are you going to convolve with sinc now? What is the function associated with this? The whole signal.
Fs of u, sir.
Huh?
Fs of u.
Fs of u. So now you tell me convolving with sinc. Which function you are going to convolve with sinc is my question. The answer is
Fs of
correct.
x.
Exactly, right. Fs of x, the sampled versions of your continuous time domain, you are convolving it with a sinc function. So what it will do, if you recollect, at integer multiples, only the sinc that has been placed at that value would contribute, and non-integer values, it would be reconstructed with the help of all the sincs put together. Hope you remember that when we discuss the sinc function reconstruction. Otherwise, just refer back to Oppenheim. Okay, so now the moment you are convolving the sampled version, okay, this one with the arrows that you are seeing here with a sinc function, right, which is coming from inverse Fourier transform of your rect function, then it would give you the whole continuous time signal. Now with that, you could compute its value at any point, in any intermediate point of these x, 2x, 3x, and so on. Okay, is everyone? So that's exactly what you would see here. That's what is going to happen here. This is your fs of x convolved with this. Okay, yeah, that's basically this f of x he has brought inside, and anyway at this point it would be equal to nx. So this is made a constant. That's all. So is everybody fine with this? What we are doing here, and why is it happening so? Any questions here? Any questions from MTech students? Who are there? Are there anyone today from MTech? 18B, I'm trying to,
Yes,
yeah.
sir.
Yes, so is that clear?
Yes, sir. Clear, sir.
Okay, good. Yeah, please, if it's not clear for you, please do not hesitate to stop me. Okay, just we can just spend few more minutes, then it could get clarified, hopefully. Right. So then after that, hope we are here. Okay, then I'll anyway share these slides, so go through it again. If it's the equations part, I'm not spending much time now because they are quite obvious. Once you look into it, you should be understanding that. Okay, then comes the sampling theorem. Okay, if they are placed overlap, if your 1 by x is not good enough, there are overlapping of copies, and then when you are doing it by 1 by x, then there is this part where both the weights are getting summed up there, right? Another example here, and what's happening in 2D. Let's say this is your Fourier domain frequency for a given signal. And then you are multiplying here with this. Okay, that would keep the, sorry, you are in the frequency domain. Okay, it is equal to convolving with this bed of nails. So once you are doing it, it would be nice if you keep plotting these things in the using MATLAB. So that convolution would give you something like this here. And then what you would do on top of it, you multiply it with this function, rect of kx of x and rect of ky of y. So that would give you two rect function multiplications. That's what you have it. So that is how you take, I hope I could draw something here as well. Okay, that's how you would take a copy of it here. And then you construct it back. Okay, let me go to normal mode. Okay.
So what was that process that was happening in the previous slide?
This one, huh?
Yeah, it's deblurring, right? Just
yeah, this looks, no, this is actually the frequency spectrum of a given signal. So it doesn't look like that when you are multiplying it.
okay, this is the bed of nails, and this is, yeah, okay, sir, got it.
Right, that's right. And then on top of it, you would be then multiplying it with rect of kx into x plus rect of ky into y. Just let me erase this out because it is carrying to the other slides as well. Okay, right. Fine. So this is again the same theorem that we have seen for 2D, slightly used a different parameters names here, conventions. Other than that, it is fine. Okay. So then this is another example of what could happen because of aliasing. Okay, those who has done DSP course have seen a very similar slide earlier. Suppose they imagine this is one signal. Okay, and imagine there is another signal here, right? So how are these two related? These two signals are related. Do you see some relation between these two signals? Assume that they expand on both sides with a similar nature. See, for example, this is one period, right, of this signal. Now, how many periods are there for the other signal by that time?
Frequency of red one is twice that of the
right. So look at now, if you are not taking enough samples, what would happen is, suppose you are taking sample here, 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 here. Is there any way you could distinguish or reconstruct back that these two signals are different? Unless you take, you decrease the rate at which you increase the rate at which you are taking samples, or decrease the distance at which you are taking samples. At least you are taking somewhere in the half here. Okay, that is what distinguishes. Otherwise you won't be able to distinguish the signals. So that's what, when you look at in the Fourier domain, it looks like an aliasing effect. So that's, then you would be eventually ending up mapping these high frequencies to low frequencies as well there. Say this also another example that tells you, so you do one thing, purposefully you don't see this part, okay, and then see how you interpret how things are going here, and then you see it then you try to interpret how things are going. So in one way, you could see here, see from here only, you observe only just this, for example. It looks like this has moved from here to here, okay, then from here to here, here to here. So that's what you would see. But yeah, without the dot, hole appears to be rotated slowly. No, sorry. So the way we interpret things without this dot is, yeah, I think we discussed it at length in our DSP course and computer vision course also, is that by default we keep interpreting to low frequencies. That's what our visual system would do that. So the way you would interpret it is, it is moving in this direction, that means anti-clockwise direction slowly. Okay, that's what you would be. This has come here, and so on. Maybe this is not the very best example. Okay, I hope some of you still remember this video. I think somebody has later thought of me. I don't remember whether they made an app similar to this. Somebody has said he has done it. Okay, so look at this. I'm sure this effect, I'm not playing it the whole thing, but let me just briefly talk about it. So this effect, you would have seen it in movies as well. So what would happen is, it looks like some parts are moving back rather than moving forward. That's because essentially something is moving, and then you are taking samples of it. That's what, at a frame rate you are taking the images. And because of that, if your frame rate is not enough, so suppose if something has started at one point and made the whole rotation, okay, and coming back to it, suppose it has made, let's say 320 degrees rotation, okay, in the clockwise direction. But the way you would interpret it is as if it is rotating in the anti-clockwise direction by 40 degrees, because that's the closest one. So we, by nature, we would try to map it to the nearest one. That's because that's equivalent to the frequency of it is less, in other words. So that's a low pass filter. So our brain inherently does low pass filter. So otherwise, even if it is, so that effect you could see in this example here. Because of that, things looks like 1 minute, I can't, yeah, it's playing now. Okay, this need to be restarted. So any questions here? I haven't touched upon few points here. I thought maybe if you already remember from our discussion, you won't have the questions. Otherwise, if you don't think about it in detail and resolve it also, in that case you should, yeah. Do you have any questions, by the way, those of you particularly who are looking into this for the first time? I'll show it again.
Which direction it will means? What is the
Yeah.
mathematical background? Can we explore,
Yes.
sir?
Yeah. 1 minute. See, how do you, first of all, maybe the question that to answer that, maybe I'll not direct, yeah, I'm not exactly answering your question, but hopefully this should give you the lead for doing that. By the way, how do you interpret whether something is moving forward or backward? See, for example, here, how do you interpret whether this is moving forward or backward? Let's say the inside rim. Is my this one visible?
Yes, sir. By
Okay.
looking the background. By looking the background.
Not really. It's not the background. So the object I am giving, okay, I'm not looking at, I'm just looking at this object only.
Yes, sir.
So then how do you interpret if something is moving forward or backward? See, basically, or let me put it in this way. See, there are different objects in the movie clip that appear, some moving forward and some moving backward. Why is it so? Why not all in the same way? Yeah, Rohit, you are saying something?
With respect to the reference.
Sorry?
With respect to the reference frame.
Yeah, means how do you interpret whether it is moving? It's still not very clear from that.
So with respect to its previous position.
Yeah, with respect to its previous is correct, but still with respect to its previous, how do you interpret? That's my question.
According to the frames per second, like
No,
how
no. Do
we
you mean
sample.
we count frames per second? No, what I'm all asking is, see, I'm not asking you why it is moving backward or forward. That's according to the frames per second. All I am asking is, how do you interpret if something is moving forward or backward? Any part here? How are you interpreting that?
It's angular speed. I think it's angular velocity. The velocity of the point we see.
Right, but angular velocity is same for everything, right? The whole
The
wheel.
velocity of that point is different, right? Because we see the V.
Okay. So,
So
but still, if you see, maybe whether I'm not very sure if that can be shown here, you consider three levels, one being low and one being high and one in the middle. But still, there could be a scenario here where the middle one could be rotating backwards, but the rest rotating forward. That's quite possible to create here.
all points have different speeds, right? So all of them appear to be different for the same frame rate that we have.
No, yeah, they are, all those points may be
So
valid.
we fix a point somewhere and we'll
Right.
see where it is going in which direction.
Exactly. Very good. That's right. See, the way we interpret whether it is moving forward or backward is you look at this nuts, okay, and then while it is rotating, you don't really know whether in the next frame, suppose if assuming it is rotating forward, there is no way you could figure out whether this nut got replaced with this nut, or assume that there is one more nut here. If we are just given this is a symmetric one rotating, so the we make an inference whether it is rotating forward or backward by just keeping track of those landmarks. That's how we do it, because it's otherwise it's very symmetric. You cannot distinguish anything there. There is nothing to distinguish the background there, background being same, circularly symmetric. Okay, but these are the points which you use. Similarly, this one is there. For example, you see something here. Similarly, you see something here and something there and something there. Okay, these are the points you would use to figure out whether it is rotating forward or backward. Okay, similarly, it comes to here. Maybe you are seeing something here, the same thing, similar structure here. So by that, you yourself draw something which is shown in the so yeah, because of this, what would happen now is you could always manipulate these points. Angular velocity is something else, but here you could, by manipulating the locations where you have these points, since by default we are we are hijacked, our recognition of its motion is hijacked by where you have those points, because that's the only way we could figure out. We only have snapshots of it. So that is what these number of points, if you notice, are different actually for various structures here, right? And that is what is causing you, or causing, of course, causing us clear all. Okay, to make certain parts rotate in the forward direction and certain parts in the backward direction. Okay, just 1 minute. Where is, okay, right. You want to go back? Okay, I should click here. Fine. Oh, so if you want, just take a look at here. See, look at here. These are the points that we would be using to, these number of points here are different and these rims are different. So because of that, you could come up with such that the way it replaces could be just backside of it, but the full rotation it might be going. Okay, this again has something to do with stroboscopic effect also. So is that clear? Yeah, you keep these 2 points in mind. That should make it clear. Yeah, any question? Hope then it is clear to everyone. Okay, that's aliasing. Okay, an example. So this is another example of a 2D case where, as you could see, copies are placed along x-axis and along y-axis. So suppose this could be your original Fourier transform of the original signal, but then if you are not taking enough samples of your spatial signal in the spatial domain, you could end up with frequencies like this, right? This should be quite obvious because you are keeping copies on all sides of it. Then this is the kind of effect you would be, what should you call this? Is this, it's, yeah. As you move, so this is a slightly a different example from a different perspective, but still explains things. See, for example, what's going to happen, this is again computer vision guys should be understanding it very clearly, and others also, it should be quite intuitive. As you move away, right, and when you are taking picture of it, the number of samples that you have for that in the image would be less, is it not? The object closer to it, like for example the background, whatever picture is there, so there the number of samples that I have for that picture versus the picture being very close here, assume that there are two pictures, okay, and then the number of samples would be obviously less there, is it not? That everybody intuitively knows it. And similar thing here, along with that, then this object is as you know, this is a 2D projection of a 3D object. Because of that, here you could nicely see them, but the moment these are all nice parallel lines actually, so the parallel lines also become this is all we studied in more detail in computer vision also. And then the number of samples being less, they no more look like squares, and everything is like you have the effects you used to get in the titles of old movies where they have all this fancy effects. So those kinds of things you have it there. So problem being not having enough number of samples in the spatial domain for that particular ones. Okay, this is another one showing you the similar effect. Suppose you this is a one interesting wave. Okay, assume that this is the kind of sinusoidal wave you have it, right? And this is a continuous time signal, and if you are trying to plot it in the MATLAB, okay, you have to plot it only at particular values of x, right? So for example, this plot has been taken at 0 is to 0.05 is to 5. So you are incrementing the values by 0.05, right? And then you are up by that way, you are going till 5. And this one, you could simulate this kind of behavior by using sine 2 power x multiplied with x. It looks like this is interesting. So so this is what you would be getting. Okay, this is sine 2 power x multiplied with x is what you would be getting. So you could already see here, if you are not taking enough samples, you would be picking up at the same at values which is constant. You won't be anymore able to track those high frequency content. So if you are using these values, this is the original graph, you this in fact would start varying quite fast, okay, because the frequency is becoming quite high here, 2 power x, okay, the frequency as x is becoming high, is becoming quite high there, right? So because of that, that should come like this. But then because of the sampling effect, you would be getting like this. Now assume that instead of 0.05, if you are using 0.1, this effect would start even further, maybe somewhere by the time you reach the middle itself, you have that, you'll be having as if there is no variation at all, as if there is a constant value itself. You can't see here, this sinusoidal variation is very clear. The variations that are going here is pretty clear, but could look like as if it's a constant value. That's because of not having taking enough samples of the signal. Now you, for example, modify it to 0.005, okay, then you have to go beyond maybe around 10 or something like that, you would be getting this effect again. But again, high frequency content, you have problem with the sampling stuff. So when it comes to anti-aliasing, when there is an aliasing, two ways you could do. One is, if you have sampling frequency in your control, increase the sampling rate, or in other words, decrease the distance at which you are taking samples. Or else, if you don't have that in this is prevention. Okay, you could or this is a cure, probably I should call it as a cure, because there is no aliasing as well. If there is, you cannot avoid that. Okay, then the kind of first aid treatment or treatment that you could do is apply a low pass filter before doing a sampling. So this is another example that explains you this process. Suppose this image you want to downsample by a factor of 4, right? Now what would happen? Again, to be very strict here, we are sampling a discrete time signal, but it's good enough. Still, you could attribute the same things to sampling a continuous time signal also. So don't worry about that. Still, all these discussion applies quite nicely there also. So you could see here, by the time you are downsampling, you are keeping copies closer. That would cause an artifact at high frequencies are lost. So high frequency is essentially the edges. So you could see the edges are getting corrupted here, are getting noise. You are getting noise with edges. So what you have to do now, assume that you don't have control over the sampling rate. You can't change it. You still want it to downsample for some reasons by 4. So what's the better thing to do now is you convolve this image with caution. So what is it? What does it mean? You are applying a low pass filtering first and making the frequencies of the signal band limited by further. You are further restricting this signal. See the kind of Gaussian you are using there. So then because of that, this is what the image you are getting. And now instead of downsampling the original image, now you downsample this image. Okay, so this definitely is better. See, there is anyway you have to pay a cost, whether you lose the fine. You have to either make it blur and then downsample, or downsample and end up with artifacts. So anyways, this is all the time, this is the best trade-off you could do. You know, let the image get blurred, but still make it a meaningful image there. Meaningful, at least better than this. Yes, somebody has a question.
So can't you interpolate it afterwards, like in order to obtain the high definition features?
So the question is, if I rephrase that question, it's as if saying that after applying a low pass filtering, okay, and I get some frequency spectrum, can I not get the original frequency spectrum? That's equal. Is it not an equivalent question to that? Look
Yes,
at
sir.
it. So yeah, I'm sure you know the answer. You don't exactly know what it is there, but nevertheless you could learn some things. Again, for example, see something like image enhancements we have done earlier, right? You are looking at where are the gradients. Still strong gradients will be there around the edges, so you could use something there to use it. You compute the edges, but again, these are all then it is equivalent to the way we still interpret this image as all these edges still we could interpret from this image. So it's more or less equivalent to that, but there is never a guarantee that you could see. For example, these finer variations, hope you could see the mouse, right? These, for example, whichever are there here, you might not get it back here. That's not possible at all. But on the other hand, this strong, so that means very high frequency content where the neighborhood itself is lost kind of stuff, you can't get it. But probably these edges, this strong edge whichever is there, you could make it much better here. But again, that's a post processing with some assumptions. Like for example, you compute the gradients there, Laplacian there, you impose on that, you could perhaps make it a bit more sharp. But still, this is making something, yeah, that's what, again, maybe your deep learning networks are now, you train them by giving such similar images, let it learn. So that's what people are doing it, right? Image that's upsampling, or there is a better word for it. What is that? You don't call it as image upsampling. High resolution images, right? You so it's like construction of high resolution images from low resolution images. That's the problem. That's the field of problem that tries to address this. But again, in principle, it is not possible throughout. Only you could do certain inferences and make it better. That's all.
Sir,
Yes. Yes, Mohammed.
In movies, how do they do image enhancements? Like in spy movies, they zoom into image, then they enhance image, and they get
No,
accurate
sorry.
information.
No, I couldn't get you. Can you please?
So like in movies, they zoom into images and they enhance and make it much more clearer with high resolution.
Right. So how do they do
Yes,
it? That's the question,
yes,
right?
yes, yes.
Yeah, that's what. So what you would be doing, so in fact, that's already has been done here. See, for example, when I'm downsampling it by a factor of 4, it cannot be of the same size, still showing it in the similar lines. So what you would do there is all your PDF file does it, is that you use, for example, bicubic interpolation is something which is commonly used. So you interpolate the values based on the values that are there in the neighboring pixels. So you use an interpolation. For example, if you look at here, in both cases, interpolation is used. Otherwise, you won't be assume that this is 100 by 100 image. So what you get out of this is actually 25 by 25 image, 1/4 of it. So it should be just 1/4 of this image, something like this of this size. But again, it has been shown here. So you use something like a bicubic interpolation there to get that image. But once your information is lost in terms of frequencies, it depends. It's very subjective on to what extent you could recover it. Is that the answer for your question?
Okay, sir.
Yeah, good. Any other?
Sir, actually, there is something known as bilateral filter.
Yeah.
So,
Okay.
so it is the equation is more or less same as Gaussian, but what it does is like it just rejects the pixels whose values differ too much from the central pixel.
Right. See,
So that's what
these are
it
all
is.
there are different optimizations. I'm just telling Gaussian as one example. There could be definitely better ways of doing it. That's not what we are going to look at here. All the point that we are going to make here is the once you apply the low pass filtering, okay, it is like given value is equivalent to rounded off value to the nearest integer. Okay, that's y equal to rounded off value to the nearest integer of x if I do it. And after doing that, can I get back my x from y? That's the question. That is irreversible. But here we make some some assumptions here. For example, the neighborhood information. Well, this might get rounded off, but how good the surrounding pixels got rounded off, you could see. And if there exists a relationship there, that's what you would like to exploit in order to get a better value. And that's exactly what interpolation does. And then there could be different ways of better than, instead of this smoothing, there could be some other smoothing to get. So one is a simple thing is a rect function, but in practice is rect possible? That's one question. If not, you would be using some other function. So there could be different permutations and combinations for this part, as well as the part here where you are zooming it out. So those things could be there. But then nevertheless, as a problem, this is a problem where the inverse of it is not possible. That's the point here. Is that fine, Sumant? Or is
Yeah,
it
yes.
okay?
Yes,
Good. So any other question or comment here? Okay. Anyway, this slide we have seen it in the earlier one itself. So where you are keeping low pass image, so you just keep the low frequencies would give you low pass filter, high frequencies, this is what. So low pass filtering is something like this. Okay. Yeah. So that's what you would be doing here. So in order to downsample by 4, instead of doing that, what you would do is convolve it with a Gaussian. Okay. And then you get a the same thing here. Okay. So by the way, this is before coming here, let me just is it clear so far? Can I stop here? So is it clear? I'll just stop the recording part here.